Okay, so in the past few videos, we've been talking about simple Monte Carlo, and we've gone through the ideas of what is simple Monte Carlo, how do you actually interpret it, how do you construct important sampling proposals in this paradigm, what are optimal proposals in this paradigm, what are the properties of simple importance samplers? For example, are they unbiased? Yes, they are. Are they consistent? Yes, they are. What does the variance of these look like? And so we've been studying some of these things. And in this particular video, we are going to go through the concepts of how do optimal proposals compare with suboptimal proposals. Okay. So we've gone through basically two main examples, code for one of which was already actually shared in the PDFs, but I'm going to go through code for that again here. And then I'm going to go through code for the normal example as well. So our first example is that of the gamma distribution, where the idea is that we are going to do, we are interested in estimating moments of a gamma distribution. And then the optimal, we figured out using math, is that the optimal proposal for estimating the kth moment of a gamma distribution is gamma alpha plus k comma beta, where the target distribution is actually gamma alpha beta. So let me just add that maybe here, just so we are clear on the notation. Okay. And so the way the code for this works is I create a function imp underscore gamma, which has the following arguments. It has argument n equals 1000, which is the number of important samples I'm going to obtain. It has alpha equals 4 by default, which is the shape parameter, beta, which is the rate parameter, moment, which is the moment I want to estimate of this target distribution, and imp.alpha, which is going to be the shape parameter of the importance distribution or the proposal. Now, the way the function works is first I'm going to draw from my importance distribution. In this case, that is a gamma distribution with imp.alpha being the shape parameter and the rate parameter being beta itself. All of these proposals are stored in the whole vector draw. And then I'm going to take draw to the power kth moment, where k now is the moment argument in this function. So in this case, by default, it's going to be the second moment. So I do x squared, that's my h of x, times my f of x, which is just a d gamma with shape equals alpha, rate equals beta, divided by gx, which is d gamma, shape equals imp dot alpha, rate equals beta. Okay. Now all of this is this fn dot value is just going to be h of x, f of x by g of x. And then I'm going to return all values in fn dot values, right? So the whole vector of the values are going to be returned in fn dot values. Okay. And when I run this, so let me close the screen back down. So I run the seed so that you and I can have the exact same answers. And then I run the function, and then I set n to be equal to 100,000 because I'm going to want 100,000 samples from this process. Okay. Now what I do is I'm going to run this because I've created a general function. I'm going to run this for different values of imp.alpha. So the first value of imp.alpha that I'm going to look at is just 4, which means that my actual target is 4, 10 according to the defaults I've stated here. And my proposal is also going to be 4, 10. Okay. Now the actual mean in this situation is actually 2. So when I say mean, I mean the second moment of this target gamma distribution is 0.2. And the sample mean of these fn dot values or imp underscore sam is actually nothing but my simple importance sampling estimator. And that turns out to be about 0.1999, very, very close to 2. So we're doing quite well. And to estimate the variance of the importance sampling estimator, we actually can do variance on the imp underscore sams. So what this does is it estimates n times the variance of hat theta g, which is n times the variance of the importance sampling estimator. See, the importance sampling estimator has variance of something divided by n, because as you get more and more samples, your variance should keep on reducing, right? So that's why there's a 1 by n on it. Now, When I do variance of imp underscore samples, it takes the sample variance of all your important samples that you've obtained, all of the h of x, f of x by g of x, and that turns out to be n times the variance of the estimator itself. Okay. When I run that, I get 0.044, which is pretty small, which means I'm doing fairly well. So my estimate is close to the truth, and the variance of the estimate is fairly small. So I have a pretty good answer. And this is not surprising because I have used the exact target distribution as my proposal distribution, which I know should work in this particular case. But this is not the optimal. The optimal, according to our known truth, is 6, 10 or alpha plus k, 10. In this case, alpha plus k is 6. So when I call my imp underscore gamma function with all the default values, I get imp underscore samp as my samples. That's a sample of length n. And mean of imp underscore samp should give me my actual estimate, which in this case is exactly 0.2. That's the actual exact answer. And more interestingly, if I look at, head of imp underscore samp, okay, I'm going to get all values of 0.2. So if I, instead of looking at the first 6 values, if I look at the first 20 values, they're all 0.2. And the reason is we went through this in the class notes, is actually h times f by g turns out to be a constant, right? So this fn dot value turns out to be a constant every time. It does not depend on the draws that you've obtained because this is the absolute optimal proposal. Which also means that the variability in all of these values is basically 0. And so when I do var or sample var of imp underscore samp, I get a number like 9.6 into 10 to the power minus 33, which is essentially 0. It's just R is having a little bit of trouble with some numerical inaccuracies. Otherwise, it should just exactly be 0. Okay. Now, why is the estimate good? The estimate is good because if I draw the density function of my target, which is this black curve, and a density function of my proposal, they're very close to each other. Now, they will not be exact. The optimal and the target will not be exact because we're trying to estimate the mean of some function h of x. Okay. And because of that h of x, the actual optimal changes because of that h of x. Okay. Again, these are the things we've gone through in our notes. Okay. Now we can do the same thing, but instead of 6 as being the shape parameter, I can give it 7 being the shape parameter of my proposal distribution. And that turns out to give mean 0.1997, which is very close to the truth of 0.2. And then the sample variance in this case turns out to be 0.0078, which is really small, smaller than 0.044. So, this choice of the shape parameter is also great, but not optimal, right? Because the optimal is 6. Now, what happens when I change the shape parameter from 7 to 100? When I do that, and I look at the actual estimate of the simple important sampling estimator, I get something that's 1.6 into 10 to the power minus 22, which is incredibly small, very far away from 0.2. Right? So actually, the estimate turns out to be really bad in this case. What happens when I look at the sample variance? Well, the sample variance is actually pretty good because the estimate is always bad. The reason that's happening is if I compare the density points, the densities, is that the red curve, which is my proposal density, is so ridiculously far away from my actual target distribution that there is no hope of actually obtaining samples from this area. Okay, from this area. So we keep continually obtaining samples from this proposal distribution and almost never obtain samples from here, which means our weights f by g are ridiculously small for all the values sampled here. And because it's so ridiculously small, our estimate is ridiculously small. Okay. Now, once in a while, like once in 1 crore, 10 crore draws, we are going to sample a value here because it is in an area of high probability, in an area of positive probability. So we will at some point draw a value here. As soon as we draw that value, it will be given such a massive mass because f is so large and g is so small that then when I calculate the mean here, it's going to be fine or unbiased, visibly unbiased, and the variance will increase again. Okay, so the problem is not that the estimator is bad. It is bad, but the problem is that our estimation of the quality of the estimator is also bad because we haven't obtained enough samples to actually get that unbiased behavior. Okay, so it's a little bit of a subtle point, and hopefully it makes sense. But that is the optimal simple important sampling description for the gamma example. Now we did another example, and that was the Gaussian or standard normal example. The optimum in that case is what turned out to be certainly not the actual target of normal 0, 1. So remember, we were interested in estimating the mean of a standard normal distribution, and unsurprisingly, given the history of what we've been doing, the actual optimal is not normal 0, 1. But actually, the universal optimal was quite complicated to figure out because it had these absolute values, and it was a little tricky. So instead of looking at the universal optimal proposal, what we did instead is we fixed a class of the importance sampling distribution. And the class of distributions we looked at was the normal distribution. Within that class of normal distributions, we found that the optimal proposal had variance of 2 for estimating the mean of a standard normal. Right? So that is really what we're going to figure out here, that how does the variance, how does the optimal proposal within this class compare to other proposals within this class? But I will stress that in this part of the code, we are no longer studying the universally optimal proposal. We are studying the optimal proposal within a nice class of distributions. Okay. So the code here, you set the seed, and then you have a function that calculates the importance sampling estimator. The function has sample size 1000 and has variance parameter. Variance of the proposal default to be 1, which means simple importance sampling is by default will be the one that's just going to be simple Monte Carlo. Then I draw my samples, normal 0, sigma dot g, which is in this case by default 1, but it could be something else when I give it another value. And then h of x times f of x by g of x is going to be stored in fn dot value. It's going to be a vector of values. And that's going to be draw, which is x times f of x divided by g of x, where remember g of x is my given choice of the proposal, which is dictated by the variance that I have given into this function. So this becomes square root sig dot g. Okay, so now I'm going to run this with the seed so that you and I have the same result. And now I'm going to get 100,000 samples from these target say simple importance samples. And then my first example is one where I just do simple Monte Carlo, which means I'm just going to draw samples from the actual target distribution and take the sample average. And when I do that, I get a number which is very close to 0. Recall that the mean of a standard normal is basically 0. It is 0. And this is fairly close to 0. And we expect this variance over here to be 1 because I'm using the simple Monte Carlo, just drawing from the target distribution. So the sample variance of the sample mean is 1 by n. So n times this is just 1. Right? When I do that, I get roughly 1. Which makes sense because this is estimating that variance of exactly 1. Okay. I can instead also set sigma squared g, which is the variance in my importance sampling proposal, to be 5. This is not the optimal according to our calculations. The optimal was 2 in the notes, but we're going to set it to 5 to see what happens. And when I find the mean of those samples, it is 0.0028. Fairly close to 0. And when I look at the variance, I've given this away here, but it actually turns out to be less than 1. It's probably significantly less than 1 because about closer to 0.9. Enough for me to conclude, that actually sigma squared g equals 5 is better than using sigma squared g equals 1. Okay? Because I am getting a reduction in the variance. Recall, All of these estimators are unbiased estimators, which means I am getting a reduction in variance, and that's going to be good for me. Now let's try sigma squared g to be equal to 0.2. I know 0.2 is not optimal, but additionally, I know for this case, the theoretical variance in this case when sigma squared g is 0.2 is infinity. Infinity. I know it's equal to infinity because I know that the integral that we were trying to solve in these calculations does not hold if sigma squared g is too small, smaller than I think 1 by square root 2. Okay. So when I run that here and I look at the mean is minus 0.087, which is no longer that close to zero, about an order of 10 or 20 farther away from zero. But most importantly, when I run variance on these, I get 1955, where the actual, just running standard Monte Carlo gives me 1. So the variance is massive. Now, in finite samples, we're never going to get infinite variance. That's not going to happen. So our best bet is to check whether the variance is, inflating ridiculously. Is it really increasing and skyballing to something ridiculous? And in this case, it is ridiculous. And this is n times the variance of the estimator, which is really, really large. But I know that my actual optimal within this family is sigma squared g equals 2. So let's see how that looks. So when I run that, and I look at the mean, well, the mean is really, really close to 0. So that's great. That's a great estimate. And then the variance of this is 0.77, which is very close to the theoretical variance of 0.78. This is different from the theoretical variance of 0.78 because, and I'm going to put this here, recall the variance is actually being estimated. We're not using the exact variance expression of the estimator because the exact variance we know in this particular case, but typically we may not know. So this is one way of estimating it. Now, in this particular case, we know the exact variance. The exact variance of the importance sampling estimator is the chosen importance sampling variance divided by 2 minus 1 by that variance cubed, whole square root. This is what we did in the notes. So if what I'm going to do next is take a grid of sigma squared values from 0.8 to 10, okay, plot on the y-axis the actual variance of the importance sampling estimators that I know I can get in closed form because of the work that I've done in the notes. And then I'm going to plot that. Okay, so on the x-axis I have sigma squared. On the y-axis I have, plot of the variance of the estimator. And I'm just going to draw a horizontal line at h equals 1 because that one line tells me that this is what I get with IIT Monte Carlo sampling. So anything above this line is worse than Monte Carlo sampling, and anything below this line is better than Monte Carlo sampling. And when I notice that about from sigma squared equals 1 to about sigma squared equals 6 or 6 point something, I get a reduction in the variance, and everywhere else the variance increases quite a bit. But more interestingly, the variance increases dramatically when it's too small. So if the proposal variance is too small, we're not going to be doing very well in our estimate. And that sort of makes sense, right? Because if the proposal variance is really small, then what we're doing is we're saying we're restricting ourselves very close to the kinds of values we are proposing, which means we're not giving it the opportunity to propose values that are far outside. And so we may be missing some aspects of our target distribution because our proposal distribution doesn't propose values too far away. Okay. So one thing to remember within this normal distribution example is that this is very much, again, optimal within this family and not universally optimal. The universal optimal we couldn't really do because it was quite difficult to implement.